part 2 of today's lecture, we're going to talk about nonparametric and gradient-based MetaLearning methods. So, as a reminder, the nonparametric part refers to how the method adapts to a new task. The MetaLearning is still parametric in the sense that there's still a deep net being learned. So the basic idea behind the nonparametric MetaLearning methods is going to be something like this. We're going to have our few-shot training set, and here I'm visualizing it as a one-shot training set, so there are 5 images, each corresponding to a different label, but in general, you might have multiple examples of each class, but here we have just one. And each of those images has some label, so L1, L2, L3, L4, and L5. So we don't know what these labels mean, they're just like integers basically, 1, 2, 3, 4, 5. And they mean different things for different tasks. And then we have our test image, and our test image has an unknown label. So what we're going to have to figure out is which of these training images has the same label as our test image. That's the basic problem that we're going to be solving during adaptation. And the way that we're going to do this is we're going to have some neural network that featurizes each of these images, that basically embeds each of these images into some feature space, and we'll call that network phi. And we'll also embed our test image. Later on, we'll talk about how we can embed the test image into a different feature space than the training images, and we'll actually switch to using F and G, where F embeds the test image and G embeds the training images. But for now, we'll just say they're all embedded into the same space, and we're going to call that space phi. And then what we're going to do is we're going to compare phi x test to the embedding of each of the training images. And intuitively, what we're going to try to do is find the nearest embedding. So in this feature space phi, does our test image lie closest to x1, x2, x3, x4, or x5? Of course, in terms of the pixels, such nearest neighbor queries might not be very meaningful, but perhaps we can meta-learn a feature space where such comparisons are meaningful. And maybe we'll find that phi x3 is the nearest neighbor to phi x test, and then the way that we'll assign the label is by just taking the label of whatever the closest image is, which in this case is x3. Okay, so why does this work? Why do nearest neighbor comparisons in this feature space actually give us the right answer? Well, in general, they don't. If we had some arbitrary feature space, this wouldn't necessarily be an effective classifier. So why does the nearest neighbor have the right class in such an approach? Well, because that's what MetaTraining is trying to do. So the key to making all this work is to be able to MetaTrain the embedding function phi so that on your MetaTraining tasks, on those tasks that you have in your MetaTraining set, this particular nearest neighbor approach produces the right answer. And if it produces the right answer on all of your MetaTraining tasks, then hopefully it will also produce the right answer in your MetaTesting tasks. This is the basic idea in this kind of few-shot MetaLearning. You need to make sure that your MetaTraining lines up with what you're going to do at MetaTest time. So if at MetaTest time you're going to do a nearest neighbor query, then as long as you train your network phi to be accurate when doing nearest neighbor queries, then your nearest neighbor queries at MetaTest time will give you the right answer. So that means that the MetaTraining process can be written like this. This is exactly the equation I had before, only before I had this phi equals f theta. Now I've just substituted that right into the optimization to make for an unconstrained problem. So theta star, where theta star represents the parameters of that embedding function phi, is the argument with respect to theta of the sum over all of your MetaTraining tasks of the loss that you get by using f theta applied to dtrain on the corresponding test set dtest, where this f theta is your learned nearest neighbor classifier, although we're going to use a kind of a soft nearest neighbor approach. So if we're using negative log likelihood loss, which is the loss that we typically use for classification, this can be rewritten as the negative of the sum over all of your tasks, I equals 1 to m, of the sum over all of the test points for that task, j equals 1 to m, of the log probability of yj test given xj test and dtrain. So you're maximizing the log probability of the label of each test point given the image for each test point and the entire training set for that task. And you're summing this over all the test points and over all the tasks. And to actually define this log probability, here's what we're going to do. We're going to define this p nearest quantity. P nearest is the probability that the training point xk train is closest to the test point xj test. And it's going to be proportional to the exponential of phi xk train transpose phi xj test. It doesn't have to be a transpose, it could be Euclidean distance or it could be cosine distance. But the point is that it's some measure of how similar phi xk train and phi xj test are. So the xk train that is whose feature representation is closest to the feature representation of xj test will have the largest dot product and therefore the largest value inside the exponential. And because this is a distribution over the training points, we normalize it by dividing by the sum of those exponentials over all the training points. So you can think of this as a softmax applied to phi xk train transpose phi xj test. If these dot products are very, very big, then the softmax would eventually approach a hardmax, meaning that there would be a weight of 1 on the nearest neighbor and 0 on everything else. But for smaller values, it'll be soft. Okay, so this is, you can think of this as basically the distribution of how likely each training point is to be the nearest neighbor to xj test. And then you can define the probability of a particular label yj test as just the sum over all the training points that have the label yj test of their probability that they're the nearest neighbor. So if you want to know what is the probability that the label is L1, well, sum over all the training points that have L1 as their label and add up their probability of being the nearest neighbor. So of course, if the point with the label L3 here has the highest probability of being the nearest neighbor, that means that the probability of its label being the correct label will also be highest. Another way you can think about it is you can take each label, and for each label you sum the probability of all the points that have that label being the nearest neighbor. And then the point that has the highest sum of probabilities, the label that has the highest sum of probabilities, is the label that you would assign to that test point. Okay, so just to recap this, we're going to compute p nearest, which is the probability of each training point being the nearest neighbor of our test point. And then we'll say that the probability of the label is a sum of the probability of each training point with that label being the nearest neighbor. So in the limit, as our softmax gets to be a hardmax, and only one point has a probability of 1 for being p nearest, then its label will also have a probability of 1 of being the correct label. So now we've devised a formulation for this log p theta yj test given xj test comma d train, and that gives us our MetaTraining objective. And because everything here is differentiable, we're using this soft nearest neighbor through which we can push gradients, we can actually optimize all of this with respect to the parameters of our embedding function phi. So the parameters theta, the only thing they affect is phi. Okay, so this is a very simple formulation for a non-parametric MetaLearning method. Now the actual methods that are used in practice are often a bit more sophisticated. So this is kind of the simplest basic version that we could devise. And now we'll talk about some actual methods that are based on this idea. The first one we'll talk about is matching networks for few-shot learning. Matching networks is very similar to the basic prototype that I had on this slide, but with a couple of modifications. And the modifications have to do with how this p nearest probability is computed. So in matching networks, instead of taking phi of xk train transpose phi of xj test, instead they have two different functions, g and f. So instead of one function phi, they have two functions g and f. And both of those functions are meta-trained. So they have different networks to embed xtrain and xtest. G embeds xtrain and f embeds xtest. The other difference that matching networks has is that both G and F are conditioned not just on xtrain and xtest, but they're also conditioned on the entire training set dtrain. The reason for doing this is because you may want to do something like a process of elimination. You might want to figure out that the way that you represent, for example, the one of the dogs on the left side here might change depending on whether all the other images are dogs or other animals. So if the entire training set is just pictures of dogs, you know that you're trying to classify different dogs, different breeds of dogs. So the representation that you would choose for one of the dogs would encode properties that are indicative of what breed it is, rather than properties that are indicative, for example, of whether it's a dog or a cat, because you know you're just trying to classify between different kinds of dogs. But if, for example, you're embedding an image of a dog and the other training images are like cats, giraffes, and hippopotamuses, then you might choose different features. You might choose features that are useful for discriminating between different kinds of animals rather than different breeds of dogs. So that's why both G and F actually depend on the entire training set, because the way that you would choose to represent XTrain and XTest might depend on what the other images actually are. Okay, so this requires us to select an architecture for G and F that can embed the corresponding XTrain K and XTest J while also taking into account the entire training set. So the particular choice that this paper makes for G is to use a bidirectional LSTM. It's a little bit complicated, I think, maybe somewhat needlessly complicated, but here's how it works. You take your training set and you run a forward LSTM. So you pick some ordering and you run that LSTM forward. You also have another LSTM that you run backward, a lot like how we did with Elmo. So these are just two separate LSTMs, a forward LSTM and a backward LSTM. And then the output of G is formed by the sum of the hidden state of the forward LSTM and the hidden state of the backward LSTM and an embedding of just that image. So there's a little convnet that embeds each image. That convnet, its output is used as input to the forward LSTM, its output is used for the backward LSTM, and it's also added to the whole embedding overall. So you run the forward LSTM on the convnet outputs, a backward LSTM, sum together their hidden states, and then also sum together the original convnet output, and that's your representation of that training point. So because the forward and backward LSTMs incorporate information about all the other points, now your embedding can be contextual. The F function could in principle work the same way, but in this paper they chose a different, more complicated representation for it. So for the F function, for some reason, they decided to use an attentional LSTM embedding. Maybe they just wanted to mix things up a little bit. So they have all of the embeddings from G, and these are formed by that bidirectional LSTM. And then after that, for every data point in D-train, they have a different time step of their attentional LSTM, where at each time step they feed in the test point, and they do attention to attend to each of the training points. So the number of time steps here is equal to the number of training points, and then the hidden state of the LSTM after these steps is the embedding of the test point. They could have used the bidirectional LSTM here too. For some reason they chose to do this attentional thing. I assume because they found it to work better. Okay, so if all the stuff on the right half of the slide is confusing to you, the high-level idea is just that they're doing basically the same thing as the standard nonparametric formula on the previous slide with two modifications. The training point and the test point are embedded using different functions, G and F respectively, and each of those embedding functions is also itself conditioned on the entire training set. So these are just two modifications that they found to work well. They might be a little bit overcomplicated, but that was kind of the recipe in this paper, and it was kind of one of the first papers to really show that this nonparametric kind of formula could be really effective. Now these days, most people don't actually use this approach. A much more widely used approach is something called prototypical networks, which actually simplifies the formula a little bit. So prototypical networks can be viewed as matching networks with two simple modifications. The first modification is that instead of doing a soft nearest neighbor, what they do is they construct a prototype for each class. So the idea is that P of y given x test is now given by a softmax over prototype vector cy. So you still embed x test with an embedding function f, but then instead of taking its dot product with g of x train k for every x train k, you instead take its dot product with cy, where cy is just the average of the embeddings of all the x train k's. And that's what's shown by the picture at the top. So whereas matching networks would dot product against each of the training points, prototypical networks would embed all the training points, average their embeddings together, and then dot product against those averages. So you can kind of think of this as a logistic regression classifier where the classifier weights are produced by averaging together the embeddings of the training points. And of course the parameters theta affect f and g. And then the second modification in prototypical networks is to get rid of all the complicated junk. So there's no longer these bidirectional LSTMs or attention. G and F only depend on X test and X train respectively. So they're no longer conditional on the entire training set, which makes this quite a bit simpler. So f of X test is a convnet, G of X train is a convnet, and that's it. So this approach is actually simpler in many ways. All right, so that's non-parametric MetaLearning methods. In the next part of this lecture, I'm going to talk about gradient-based MetaLearning methods. And these, at first, will seem like they operate on very different principles, but we'll see towards the end that in many ways they actually have a lot of similarities. To set up the motivation for gradient-based MetaLearning, let's go back to something that we've already learned about. Let's go back to representations. We've talked before about how if you take a very large data set like ImageNet, and you train a large neural network on it, like VGG or ResNet, you can fine-tune that network to solve other tasks. So you can basically pull out the features in that network, and you can fine-tune with a smaller number of data points to solve some smaller task, like, for example, fine-grained classification. So the question we could ask here is pre-training actually just a type of MetaLearning? It seems to have a very similar formula. You're going to use a very large, diverse prior data set to get something that you can then use to solve visual recognition tasks more efficiently by pre-training and then fine-tuning. Pre-training gives you better features which enable more efficient learning of new tasks. The idea in gradient-based MetaLearning is to basically leverage this recipe, but modify the pre-training phase so that it explicitly optimizes for better fine-tuning. So here's how we can frame MetaLearning as an optimization problem. This is the abstract view of MetaLearning that we had in part 1. What if f theta detrain is just a fine-tuning algorithm? So before f theta detrain was something like an RNN that reads in the training set. What if we actually make f theta detrain be something like a gradient step of gradient descent? So f theta detrain is theta, which is the parameters of a neural net, minus some learning rate alpha times grad theta L applied to detrain. And it could be multiple gradient steps in general. Right? As long as it's a fixed number of gradient steps, that is a function that you can unroll, you can evaluate it, and it's just a well-defined function. Just like an RNN is a well-defined function, gradient descent is a well-defined function. And crucially, this can be trained the same way as any other neural network, by implementing gradient descent as a computation graph in PyTorch or TensorFlow, and then running backpropagation through gradient descent. So the MetaTraining process involves optimizing theta so that these gradient steps on theta result in a parameter vector theta that does well on d-test. So it perhaps helps to illustrate this with pictures. So this is a method called model agnostic MetaLearning, or MAML, and here's how it works. Let's say that you have your convnet and it has parameters theta. So it's just a regular convnet, nothing special. It takes in one image and outputs one label. If you want to train this convnet on a single task, each training step will be a gradient descent step on the loss on the training set. If you're doing mini batches, maybe you actually subsample the training set, but basically that's what it's going to be. It's going to be theta becomes theta minus learning rate alpha times grad theta L theta comma detrain, where L theta comma detrain is a sum over all the data points in detrain of their negative log likelihood. With MetaLearning, what we'll do instead is we'll actually train the network so that a gradient step on each of the tasks maximally reduces the loss on that task. So now every MetaTraining step will do theta minus some MetaLearning rate beta times the sum over all the tasks of the gradient of the loss on the test set dtest I with the parameters theta minus alpha grad theta L theta comma dtrain. So the parameters, the neural net parameters we plug into the loss, into the outer loss, are the parameters we get by taking one gradient step on the training set. And then we evaluate the loss of those updated parameters on the test set for that same task. Now, every task is going to have a different parameter vector after the update. So before the update, all the parameters are the same, but after the update on task I, you get a different parameter vector phi I, and it's specific to that task. And it's the loss of that phi I that we want to minimize. Another way of thinking about this is that we're trying to find a parameter vector theta from which we can fine-tune as well as possible to each possible task in our MetaTraining set. And remember, I draw all these pictures for the case where you take one gradient step to adapt, but in general, of course, you might take many more. In practical implementations of MAML, it's pretty common to take between 5 and 10 gradient steps. Still much less than what you would do in full non-meta-trained fine-tuning. So model-agnostic MetaLearning actually prepares the network to adapt with a very small number of gradient steps, but typically more than one. So you can think of this visually like this. You could imagine that this thick line theta represents your path through the parameter space during MetaTraining. And for every task, and in this case there are 3 tasks, you consider the parameters that you'll get after you take one gradient step in the direction of the gradient for that task. So that's represented by the little arrows. And you want to bring those updated parameters as close as possible to the optimal parameters for those tasks. So you're moving through this space so that one gradient step from the theta values aligns you as closely as possible to the optimal thetas for each of those tasks. Okay? So at a high level, what this is doing is that it's meta-training the model to fine-tune very well. Very well in the sense that the loss on the corresponding task you just fine-tuned on should be low using its test set. Okay, so what did we just do? Okay, this kind of fine-tuning intuition, that makes sense, but how does this map onto all these other meta-learning methods that we learned about? Well, let's go back to basics. Supervised learning, learn a function f of x that gives you y. Supervised meta-learning, learn a function f of dtrain comma x that maps to y. Model-agnostic MetaLearning is just a particular choice for this function. It's just a very peculiar choice. It's a choice where f mammal of dtrain comma x is given by f theta prime of x, where theta prime is obtained by taking a gradient step on dtrain. But it's just a function. The fact that it has gradient descent embedded in there for the purposes of MetaLearning is not actually all that important. It's just a function, which means you can code it up in PyTorch or TensorFlow, and you can treat it as just another computation graph, and your autodiff package like PyTorch or TensorFlow can actually backpropagate through this gradient descent procedure. And the only detail about this is that it will involve computing second derivatives through your neural net, so you need to make sure that your autodiff package can compute second derivatives. It actually turns out that you don't need anything other than second derivatives. It might be tempting to imagine that if you take like 3 gradient steps, you need like 4th derivatives, but that's not true actually. You only ever need second derivatives. Now, you might then ask, well, if it's just another computation graph, why do it this way? Well, it turns out that this approach actually has a very favorable inductive bias. Inductive bias means that this design is well suited to solving learning problems. Why? Well, because it's doing gradient descent. This matters when the task you actually want to adapt to is not exactly from the same distribution as the tasks that you meta-trained on. So the idea is that if you see a task that's similar to the tasks you've seen before, this will of course work very well, but if you see tasks that are a little bit different, this will still work okay because in the end all you're doing when you adapt to a new task is running gradient descent. Okay. So why does this work? Well, if we think back to the something like the black box MetaLearning methods we talked about before, we could say, well, what part of those algorithms implements the learned learning algorithm? Well, the learned learning algorithm is just running the RNN forward. So running, presumably somewhere implicitly inside that neural net, inside of its weights, is the understanding of how to adapt to a new task. So the learned learning algorithm just corresponds to running your RNN forward. But if we are going to say this is a learned learning algorithm, we can start asking questions about it. We can ask, like, does it converge? Well, kind of, because you run your RNN forward and you get an answer. What does it converge to? Well, we don't know, because it's going to be the result of that RNN. If your new task is in distribution, it should generalize. If your new task is not in distribution, then you might get some unexpected answer, as we learned about before. And if the answer you get is not good enough, you don't really have much recourse. You can't run the RNN for longer. That doesn't really make sense. Once the RNN is read in the training set, that's all you get. In contrast, with the gradient-based approach, it's still a computation graph, just a different one, the one that has this gradient operator in it. And we can ask the same questions about it. We can say, does it converge? And it does, because it's gradient descent. What does it converge to? Well, it converges to a local optimum for your new task, at least in terms of training error, because it's gradient descent. And if it's not good enough, if the result that you get is not good enough, then you can just keep taking more gradient steps, because it's just gradient descent. And in fact, with MAML, that turns out to be a very effective strategy. Oftentimes, you can get better solutions with MAML if you take more gradient descent steps when adapting to a new task than the number of gradient descent steps that you took during MetaTraining. And that can work actually quite well. Now, we can ask another question. We can ask a question about universality. This is a somewhat subtle question, but it basically boils down to this. Can your MetaLearning algorithm learn any algorithm? Okay, so maybe adapting to this particular task requires some really complicated mathematical operation. Can your MetaLearning algorithm actually learn that complicated mathematical operation? More precisely, this is analogous to saying, can it represent any function of dtrain and x? This is a fairly subtle question. The reason this question is important is because if your method is universal, that means if you give it enough parameters, it can basically learn any learning algorithm. And you want that because you would like to use very large meta-training sets with many, many tasks to figure out the best adaptation procedure possible. The black box meta-learning methods are universal in the sense that if you have very, very large RNNs, in principle they can represent any function. It is not at all obvious that MAML, that model-agnostic meta-learning, or gradient-based meta-learning, is in fact universal, because it's constrained to use gradient descent to adapt to a new task. But it actually turns out that both the black box meta-learning method and the gradient descent method is universal, which is a somewhat surprising fact, but it's actually true. Essentially, this amounts to saying that if you meta-train the initial parameters of a deep net, you can actually torture that deep net so that gradient descent updates to that deep net do anything you want. You could even torture it so that it goes backwards. You can actually torture it so that a gradient update goes in the opposite direction. It's a little crazy how this could happen, but the key to it is that your neural net has many, many layers, and those layers can affect the gradients at other layers. Okay, so to summarize, we learned about three classes of meta-learning methods: black box meta-learning methods, which use some kind of sequence model to read in the training set; nonparametric meta-learning methods that somehow embed all the training points and do some variant of soft nearest neighbor to match them up to the test point; and gradient-based meta-learning methods which adapt to a new task with fine-tuning, and then during meta-training they train parameters so that that fine-tuning process works very well. Now, these three classes of approaches have a number of trade-offs. The black box meta-learning methods are, in some sense, conceptually very simple. You don't even really need any special algorithm for them. All you do is you set up some kind of sequence model that can read in a training set, and then you just train it as supervised learning at the meta level. So you basically run supervised learning where data points are tasks. Every data point is a training set and a test point. So conceptually, it's very simple to set this up. These methods benefit from advances in sequence models. So if you use a transformer rather than an LSTM, it'll work better. So all those developments in developing better sequence models will help with these black box approaches. But they do also have a number of shortcomings. First, they have minimal inductive bias, in the sense that everything has to be meta-learned. There are a number of things we know about learning processes that are ignored by these methods. For example, there's no prior knowledge that the relationship between x and y on the training set is the same as the relationship between x and y on the test set. Like essentially the model doesn't know that the training x's and the training y's are of a similar data type as the test x's and the test y's. As far as the model is concerned, it just has to read in this thing called a training set, get some kind of quantity out of it, and then use that on the test set. The fact that both the training set and the test set correspond to images where the mapping between the image and the label is the same function is completely unknown to this model. It has to actually learn that as well. It's also quite hard to scale these types of methods to medium shot. So if you have, let's say, 10-shot, 10-way classification, you have 100 training points. You can probably read in 100 training points with a sequence model. But if you have 100-shot, 100-way classification, now you're trying to read in 10,000 training points. That's still, 10,000 training points might not be enough to train a neural net from scratch, so you might still want to do MetaLearning, but it would be very hard to do that with a black box MetaLearning method. The nonparametric methods have their own trade-offs. They can work very well by combining some inductive bias in this kind of nearest neighbor sense with easy end-to-end optimization. So they typically present, relatively easy end-to-end optimization problems, and they use something about the structure of the learning problem, so they're kind of a nice compromise. Generally, such methods, though, are restricted to classification. It's hard to extend them to other settings like regression or reinforcement learning, which makes them difficult to apply more broadly. But for classification, they can work very well. They also require somewhat specialized architectures, so it's a little harder for these nonparametric methods to benefit as much from developments in other areas. Gradient-based MetaLearning offers some other trade-offs. One big advantage of model-agnostic MetaLearning, as the name might imply, is that it's easy to apply to any architecture or any loss function. Basically, it doesn't require any special architectural changes. You can just use a regular architecture. You have an architecture that you use for regular image classification like VGG, you can do MetaLearning with it. So that can be very convenient. You can just take an architecture that you already have that works well for a non-MetaLearning problem and then just apply this MetaLearning approach to it. And you can also do this pretty easily for reinforcement learning, regression, other types of problem formulations. Because the adaptation is done with gradient descent, you also get good generalization to out-of-domain tasks. So if the task changes a little bit, kind of at worst, the method is just doing fine-tuning. But there are also a number of downsides. I apologize, these are a little cut off, but I'll read them to you. So one downside is that MetaTraining is harder. The MetaTraining optimization problem is harder because it requires these second derivatives, and it can be numerically a little bit unstable, which in practice means that it is more difficult to select appropriate hyperparameters for your optimizer. So it requires a little bit more tuning. And of course, it requires second derivatives, and you need to make sure that your auditive package supports second derivatives. So these are generally the trade-offs for these methods. In terms of which ones tend to work best, it seems to be a little problem dependent. So typically, these days, something like the nonparametric methods or the gradient-based methods tend to attain the best performance on few-shot image recognition benchmarks, and which one it is seems to change year to year.